In this short video we are going to look at the language of sequences and series and also some of the simple properties of sigma notation. A sequence then is simply a set of numbers in a given order, and these numbers may be given by a rule or form an algebraic pattern or may be random or apparently random. So for example, the sequence 3, 6, 9, 12, 15, 18, 21 is the sequence of multiples of 3. The sequence given by the rule xn equals n squared has got a first term of 1, second term of 2 squared, which is 4, third term is 3 squared, which is 9, fourth term is 4 squared, which is 16, and so on. And this is the sequence of square numbers. We can have a sequence given by a inductive rule. So we're given the first value y1 equals 1, and to get the next value in the sequence we have to take twice the previous value in the sequence and add 1. We know that y1 is 1, so the second value is going to be 2 times 1 add 1, which is 3. The third value is going to be 2 times the second value add 1, so that's 2 times 3 add 1, which is 7. The fourth value is going to be 2 times the third value add 1, so that's 2 times 7 add 1, which is 15, and so on. And we may have a sequence like 1, 4, 1, 5, 9, 2, 6, 5, 3, and that could be a sequence of random single digit numbers, or it could possibly be the sequence formed by the decimal digits of pi. We don't know. A series is simply the sum of all or some of the terms of a sequence. So the series 3 plus 6 plus 9 plus 12 plus 15 is a series consisting of the sum of the first 5 multiples of 3. 1 plus 4 plus 9 plus 16 all the way up to 100 is the series consisting of the sum of the first 10 square numbers. 36 plus 49 plus 64 all the way up to 400 is a series consisting of the sum of the 6th to the 20th inclusive square numbers. And if we've got a sequence given by the terms A1, A2, A3, etc., then A1 plus A2 plus A3 plus A4 plus A5 plus A6 is the series consisting of the sum of the first 6 terms of the sequence. And similarly, A21 plus A22 plus A23 plus A24 plus A25 plus A26 is a series consisting of the sum of the 21st to the 26th inclusive terms of the series. You'll probably have already met the sigma notation in some of your other work and know that the Greek capital letter sigma, which is the Greek letter S, is used to stand for sum of. So if we have sigma from r equals 1 to 10 of r cubed, we read that as the sum through integer values of r between 1 and 10 inclusive of r cubed. So what that means is that we are adding up the values of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed all the way up to and including 10 cubed. Similarly, if we have the expression the sum, so sigma between r equals 5 and 9 of r squared times r plus 3, we can read that as being the sum through integer values of r starting at 5 and going up to and including 9 of the values of r squared times by r plus 3. So that means that what we've got is we've got 5 squared times 8 plus 6 squared times 9 plus 7 squared times 10 plus 8 squared times 11 plus 9 squared times 12. If we've got a sequence of numbers A1, A2, A3, etc., then sigma from r equals 3 to 20 of AR is shorthand for A3 plus A4 plus A5 all the way up to and including A20. Now if we've got the series 3 plus 6 plus 9 plus 12 plus 15, we can see that that is the sum of the first 5 multiples of 3. So we can write that as being the sum between r equals 1 and 5 of 3r. If we've got 1 plus 4 plus 9 plus 16 all the way up to 100, we can see that we're adding up the first 10 square numbers. So we can write that as being the sum between r equals 1 and 10 of r squared. If we've got 36 plus 49 plus 64 all the way up to 400 as our series, then we can see that is the sum between r equals 6 and r equals 20 of r squared. If we've got A1 plus A2 plus A3 plus A4 plus A5 plus A6, then that's the sum of the first 6 numbers of a sequence. So we can write that as being the sum between r equals 1 and 6 of AR. And if we've got A21 plus A22 plus A23 plus A24 plus A25 plus A26, then we can write that as being the sum between r equals 21 and 26 of AR. Now there are some really important properties of sigma notation that we just need to establish and make sure that we understand. So let's suppose we've got two sequences of numbers, one given by A1, A2, A3, etc., the other one given by B1, B2, B3, etc., and that alpha and beta are just two constant numbers. Then, first of all, if we've got the sum between r equals 1 and n of AR plus BR, well, that is my shorthand for A1 plus B1 added to A2 plus B2, added up all the way along until we come to AN plus BN. Now, thinking about addition, we could obviously just add all the A's up together and then add all of the B's up together. So we could rewrite that as being A1 plus A2 plus all the way along to AN, together with, and then adding on, B1 plus B2 all the way up to BN. Which of course is just the same thing as the sum between 1 and n of ARs added to the sum between r equals 1 and n of the BRs. So that's the first of our three properties. The second one, if I have got the sum between 1 and n of alpha, that's a constant number, remember, times AR, then that stands for alpha A1, add alpha A2, add alpha A3, all the way along until alpha times AN. And of course, we've got a common factor there of alpha. So if we extract the common factor of alpha, we've got alpha times A1 plus A2 all the way along to AN, which of course is just alpha times by the sum between r equals 1 and n of AR. And that's our second property of sigma notation. And the third property is that if beta is a constant, then the sum between r equals 1 and n of beta is just going to be beta when r equals 1, add beta when r equals 2, add beta when r equals 3, all the way along until we add beta when r equals n. So all we're going to have is n lots of beta. So the sum between r equals 1 and n of beta is just going to be n times beta. We can summarize these properties of sigma notation on this slide, and we'll be making use of these properties quite a lot in the next 2 videos after this one. So it's worth becoming familiar with these properties. So let's have a look at a quick example. So use the information that the sum between r equals 1 and 10 of r squared is 385, and the sum between r equals 1 and 10 of r cubed is 3025. To deduce the values, first of all, the sum between r equals 1 and 10 of r squared plus r cubed. Well, the sum between 1 and 10 of r squared plus r cubed is exactly the same as the sum between r equals 1 and 10 of r squared plus the sum between r equals 1 and 10 of r cubed. And that's using property 1. So that is just 385 plus 3025, which gives us 3410. Secondly, we've got the sum between r equals 1 and 10 of 3r squared. So that is, by property 2, exactly the same thing as 3 times the sum between r equals 1 and 10 of r squared. So that is 3 times 385, which is 1155. The sum between r equals 1 and 10 of r squared plus 5 is, first of all, using property 1, the same thing as the sum between r equals 1 and 10 of r squared plus the sum between r equals 1 and 10 of 5. The sum between r equals 1 and 10 of r squared we know is 385. The sum between 1 and 10 r equals 1 and 10 of 5 just means that I've got 5 plus 5 plus 5 plus 5 10 times over, so that's just going to give me 5 times 10. So that's using property 3 there, and we're ending up there with 435. And finally, we've got the sum between r equals 1 and 10 of 2r cubed minus 3r squared plus 15. Then, using properties 1 and 2, we can say that that's the same thing as 2 times the sum between r equals 1 and 10 of r cubed. Take away 3 times the sum between r equals 1 and 10 of r squared, plus the sum between r equals 1 and 10 of 15. So that's going to be 2 times 3025 minus 3 times 385, plus then the sum between r equals 1 and 10 of 15 is going to be 15 plus 15 plus 15 10 times over, so that's going to be 15 times 10 or 150. So altogether there we end up with 5045. So that just finishes our initial look at the properties of sequences, series and sigma notation.